In real research problems, we rarely have the full population. In fact, we rarely have many samples. We really just have one sample from the population. When we have only one sample, there are several dangers. There's danger that our sample is going to differ from the population due to randomness in who's chosen. This is pretty much unavoidable because randomness in who's included in the sample is inherent in the design of a sample. There's also differences between our estimate and what the sample might imply based on the estimator function that we apply. This is the deterministic procedures that link us from that sample to the estimate. So to produce credible science, we have to think about both sources of error. We have to think about the errors that come when our sample may not tell us perfect answers about the population, and we also want to make it very clear what deterministic procedures we've applied to link from our sample to our estimate. In this video, we'll talk about both of these by continuing our baseball players example. So this is within population sampling in the baseball players example, if you go down to the danger of one sample. Here I want to ask a question about pitchers. So on the right in the slides, you see a scatter plot of some pitchers' salaries. So these are 40 pitchers from MLB active opening day rosters in 2023. And we see here that the right-handed pitchers, they have much higher salaries than the left-handed pitchers. And you might wonder why this would be the case. And in fact, if we summarize these, we can see that the mean here is millions of dollars higher for the right-handed pitchers than the left-handed pitchers. And the difference here is statistically significant if I carry out a t-test. So this is just a sample of 40 out of all the Major League Baseball pitchers. So you could ask yourself, why might right-handed pitchers earn more? We could probably tell a lot of stories. Maybe there are more right-handed batters, and right-handed pitchers have an advantage against right-handed batters because they're throwing from the same side where the player is swinging. We are probably pretty good at coming up with reasons why right-handed pitchers might earn more. So now over here in the website, I'm going to show you a little bit about how I worked on this example. So here I created a data frame of pitchers. I started with our baseball data set, which you can load with instructions further up on the website. And then I filtered to the pitchers, the left-handed pitchers and the right-handed pitchers. Then I'm going to set my random seed in my computer. So if you run this code, it just tells your computer where to start when generating random numbers. And this ensures that when we draw a random sample, we'll get the same one every time if we started with the same random seed. So then I'm going to draw a sample of 40 pitchers. So here I have my pitchers, and I'm going to sample 40 of them. And look at their difference in mean salary. And I realized when I made this graph and when I made this, I actually did different runs. In this example, the left-handed pitchers are making $9.6 million, and the right-handed pitchers are making only $3 million. So if you got this result, you could probably also tell a story about why the left-handed pitchers would have higher salaries. Maybe they're rarer in the population, and every team needs some left-handed pitchers in order to go up against the left-handed batters. And so it would make sense that because there's scarcity, the left-handed pitchers might end up earning more. Okay, so those are two stories where I drew one sample of 40 pitchers from the population. I found a big difference in average salaries, and I was able to tell you a story. Over here in the slides, it was about why right-handed pitchers earn more. Over here in the website, it's why left-handed pitchers earn more. So what happens if we repeat this process many times? I'm going to show you what happens when we take 1,000 samples of 40 pitchers from the population and we look at the distribution of estimates. So here's the sample distribution of estimates. The estimates that are green are statistically significant, and the ones that are gray are not. And what you see is that there's really a random scatter. On the y-axis, we have the difference in salary, the left minus the right-handed pitchers. And we see that most of them are near zero, and they're kind of scattered above zero and below zero. But by random chance, you sometimes have a point like this one, where the left-handed pitchers earn way more than the right-handed pitchers among those you've sampled. And sometimes we have a point down here like this one, where the left-handed pitchers earn way less than the right-handed pitchers among those who you've sampled. And this is the danger of one sample. In practice, we never get to see this whole distribution. You may only see one point, like this one up here. And if there's a huge surprising difference there, you might be more likely to pay attention to that point and come up with theories about why it should be the case. So if I come back to the slides here, you can do this on the website where you create your own samples and create a plot similar to that if you'd like. The fundamentals of what's going on here are also the fundamentals of what's known as the replication crisis in science. And there are a few key inputs. So first off, unless we see the population, every estimate that we make involves some noise. That's randomness in which people are included in the sample. Second, surprising findings yield big rewards. If it was true that I discovered that the left-handed pitchers earned much more than the right-handed pitchers, I might be able to write that up in a newspaper article. As a scientist, if I find a surprising finding, I might be able to write lots of published papers. Those papers might help me land a good job and achieve tenure, and they might do a lot for my career. There are big rewards for surprising findings. Unsurprising findings, like all these gray dots, they just get ignored. And here we run into a danger, which is that science may be just discovering noise. If we have thousands of labs running different samples and they get this kind of distribution of estimates, and the gray ones get ignored, and the green ones out in the extremes, they get a lot of attention and make people's careers, then we might actually not have found anything about the world. We just have a bunch of people playing this game where we produce results. So this is not just an abstract problem. This is a problem that's applied throughout many of the sciences and has gotten a lot of attention in recent years. So as one example, in 2011, Daryl Bem wrote this psychology paper running experiments that brought people into the lab and then saw whether they could anticipate future events. So these experiments sought to test extrasensory perception, like, do you know that the future is coming? And the results showed significant evidence that participants could anticipate the future. So here's a science paper where the author comments about how this example has really spurred some of the replication crisis, because people now realize that if you can prove things with science that are definitely not true, maybe what we're doing is just discovering noise. So this is true across lots of studies. The ESP one is particularly alarming, but there's here an evaluation of the replicability of many social science experiments published in top journals, and here's a link to a New York Times essay by Andrew Gelman about what's going on in the replication crisis and what we could do to fix it. So broadly, this is a problem that's really hard to avoid. It's a problem that's inherent in stochasticness in our sample estimates and in our human tendency as well-meaning researchers to come up with stories for whatever we find in our data. If we think a little bit about what we could do to avoid the replication crisis, there's not really clear answers. There's a few things we could do. So one is we could try to work with very large samples so that our sampling variability is much smaller. The more well-powered our studies are, the less likely we are to find surprising things by random chance. Second, we could work on replication projects. When I come to you with evidence that the left-handed pitchers make a lot more than the right-handed pitchers, you might go draw your own sample and evaluate that claim in your sample. Does it hold there? In this case, this could reveal that what we found in the first sample was really not something true about the world, but instead something random based on who happened to be chosen for the sample. The replication crisis, as I've just discussed it, is a danger about the link between the population and the sample. Now there is also this second link between the sample and the estimate. This link is one that you can make much more cleanly with very straightforward approaches. In particular, you can do this with your Quarto documents, where your code shows exactly the steps you use to produce an estimate. Now, reproducibility, this link between the sample and the estimate, it's not always a given. Sometimes there are many ways one could answer a question. So as an example of this, suppose you asked, what is a typical salary in the 3 highest paying teams in American baseball? Go ahead and use the whole population, summarize salaries grouped by teams, and then think about what your answer would be. What's a typical salary in the 3 highest paying teams in American baseball? So if you've had a chance to do that, I'm now about to show you the results. So there are several ways you could answer this question. If you just took the mean salary of the top 3 teams, you would get the New York Mets, the New York Yankees, and Philadelphia. If you took the median salary, you'd get the Mets, the White Sox, and Toronto. And it's not clear if typical salary needs to mean mean or median. If one person says that Toronto's in the mix and the other says that Philadelphia is in the mix, then it's really nice if you've shared your code, because then it becomes clear that the first person said that they were going to use the median and the second said, let's use the mean. Now you might also look at this and say, well, Toronto, that's not really a team in American baseball. That's a Canadian team. So maybe a third person says, well, the answer is the Mets, the White Sox, and San Diego, because we're going to throw Toronto out since they're a Canadian team. The answer, what is a typical salary in the 3 highest paying teams in American baseball, can be provided in many ways. So this is a reason for using Quarto, because you can write up your explanations in the white part of the document, and you can also provide your code in the gray part of the document. If I came to you with one of these answers in a Quarto document, you could know exactly how I came to that answer because your code is right there. So this is it for the dangers of one sample. There are dangers that come from randomness in who's in the sample among those in the population, and there are dangers in when we make a claim, an estimate from a sample, and it's not clear how we got that claim from the sample. Generally, for credible science, we need to think about both of these, both sources of statistical uncertainty from random sampling, and also make sure we have a really clear deterministic link from that sample to the estimate. In the next video, we'll talk about the future of survey sampling.